Hi everyone, today we're going to go behind the scenes of the file system. We're going to just use some commands which might become handy and beneficial for you to just see, for example, how an inode looks like exactly, or like what system calls are used when we create a file or read a file. So the first command that might be useful for you guys is the stat command. So let's say we have some random file foo. Let's read it first so you know what it looks like. It's basically 5 characters, right? It just says hello. So the stat command is used to kind of read the file node. Sorry, the inode, not the file node. It reads the inode and like its metadata. So it's 6 bytes, which makes sense because it's 5 characters, meaning 5 bytes, right? If you remember in C, each character is 1 byte, and then there is an implicit end of line here somewhere, which is 1 character, right? The \n is basically an extra character, so it is 6 bytes, and that's correct. So you could also see, for example, the type, which is a regular file, and the inode number is here, and you have like other metadata like the user ID that created it, or the group ID, and the permissions for this file, if you have read access, write access, or what users have read or write access to it, etc. And then you have like the access dates, the modified dates, the birth dates, and so on. If we do, for example, a directory, let's say my projects directory, you would see that again, like the main difference is this one, right? You could see it's of the type a directory. You could further see that here, where the first character specifies the type of file, if it's a directory or not, and later we'll see if it's, for example, a symbolic link or not. So speaking of which, let's now move on to links and see how they look like using stat. So if let's say you make a symbolic, let's say you make a hard link, foo2, right? So foo2 would be a hard link to foo. In hard link, they are essentially the same file. So what does that mean exactly when I say this? Let's say we do stat foo2, and we also do foo. So the hard link we just created has the exact same file size. It has like literally everything is the same, even the inode number. This means that they are literally the same file. We basically mapped a new name, foo2, to the same inode. This is what's happening. And in our directory we have that. Like we have 2 entries referring to the same inode. That's basically what's happening underneath. The only difference for the inode is this special field. So in like file systems, we keep a reference count to a file. So every hard link you create, let's create another one, foo3. So if we do foo, you could see now that the number of links increased to 3. That's because we have basically 3 file names pointing to the same inode. If we delete like foo3, let's clear this, stat foo, now it's decreased to 2, and basically the file system will delete the file itself, right? It will release or unallocate the blocks and like the inode and everything when the number of links are 0. So if we do foo2 now, and let's just do foo, we no longer have that inode, right? It doesn't exist, and basically now it's unallocated. Let's do a symbolic link, which is a bit different in how it works. So let's say let me create foo now. So now let's move on to symbolic links and see how they look like, right? So let's create like a new file. Let's call it this time, I don't know, test, and we have stat test. So again, it's a regular file with some number of bytes, which is 6. Let's do lns test2. Now let's see what test2 looks like, since it's a symbolic link. First of all, you would notice that it is of different size. Essentially, a symbolic link file is a file that contains the path to the original file, and that's why it's 4 characters. Why? Because it's pointing to test itself, and it's again 4 bytes or 4 characters. And you could see again another difference which is important is that it is of type symbolic link. In contrast to a hard link file, which was a regular file itself, right? Just what we talked about. This is a symbolic link file, which is totally different. And again, the number of links, let's just check like test. So you could see the number of links is still 1. And you could see also that the inode numbers are different because test2 as a symbolic link file is a completely different inode and has its own things. You would also notice here we have L, which is specifying it's a link file again. Just as we have D for directories, for symbolic links, we have L. So, you could just have this in mind. It could become useful when you want to just get more practical with how you want to see your file system works. Let's now move on to tracing, basically the system calls when we write or read some file. Let's just create some file, I don't know, hello and foo again, and we will use strace to read foo. If we do cat foo, obviously it's just going to be what's in the file, but if we use strace before that, wow, okay, so you could see we have a huge list of system calls. Each line is an individual system call, and you could just basically see the the flow of operation, right? Now the thing is that we can actually make this much simpler by filtering out any unnecessary system calls that are not relevant to what we want to trace. We could just read the or keep the opens and reads and writes and so on. And also one other point that might be beneficial for you to know is that you usually might see, or even in our videos previously, you saw that we said we use open to open files, but we are using open at here, and that's basically the reason behind this is open at is kind of a modern wrapper. Like in modern systems, open at is like a wrapper over open, which makes these operations more safe and secure. It has some, I guess, security checks underneath, like in the underlying implementation. So we can see some opens when tracing any dynamically linked program. So they're not like the actual I/O operations of our command cat, but it's more like loading local data from libc and stuff. And we can safely skim over it and just start our tracing from here, which is the actual I/O operations we care about. You could see that we call open at, and the first argument is saying the path is relevant to the current working directory, which is foo, right? It's not an absolute path, as you can see, and we're only opening it with the permission to read only, so we can't write to it. Okay, so you could see that, for example, we have read with file descriptor 3. How do we know it's file descriptor 3 that is pointing to our file we just are reading? From here, actually, we have 3, which is the file descriptor, as a return value, and that always happens when you open a file, right? It gives you, if you write a C program, you probably want to have a file descriptor variable to keep track of the open file, and then use that to read and write to it. You might have also noticed, if you know about file descriptors in a Unix-based system, that file descriptors 0, 1, and 2 are reserved specially for standard input, standard output, and standard error. So that's why any file you open, even though foo is the first file we're opening, is going to have file descriptor 3, not 0. And so that's also something else you want to watch out for. Again, back to read. We read file descriptor 3, and this is basically the data we're reading, and the buffer size is around 262 kilobytes, right? So if our file was very big and we had lots of, I don't know, text in it, if we went over this limit, the file system would call another read operation to read the extra information past the 262 kilobyte basically threshold. And even if it was, let's say, even larger than 2 times 262 kilobytes, it would do a third read and so on. And here you could also see that we have 6 as a return value, which tells us that 6 bytes has been read. This is very important because when we have the next read operation, we actually need to know how many bytes we've read so far. So like 6 would be offset, or let's say 262 kilobytes would be the offset of the second read operation and so on. And so interesting, we have a write operation, but note that we are writing to the standard output, so it's like file descriptor 1. And this is because we are printing out on the terminal, so it needs to write actually the read data into it. So it's like reading hello, it's writing hello to with 6, like it's reading it's writing 6 bytes, which the buffer has like the data hello into file descriptor 1, which is the standard output. Like this part is probably some terminal issue in rendering, and it also returns a 6 as its return value because we have written 6 bytes essentially. And finally we have a let's say a final read command or system call from the same file, and this is actually saying that we have reached the end of file, so we read end of file, which is like a special character, and it will return 0 bytes. So when this part is reached, the file system knows that we are done with reading and writing to the standard output, and we can safely close file descriptor 3. We close the file, and then we also close the standard output and standard error because we're done, and then it safely exits the command, let's say. So strace is another interesting case, and you want to just use it to, you could try it actually using it on when you, for example, strace, let's say e open at, but when you do echo hello, whoops, food 2, right? So you could just trace it to see how your file system works when you're writing to a new file too. It's a cool tool. You could also use it for a variety of other operations you're using, maybe your own programs even. When you're running a program, you want to see what's happening underneath, especially if it's a low-level program, let's say in C or Rust or whatever. So that kind of concludes this video. I hope you enjoyed it, and if you liked it, please like and subscribe if you want more content like this. I'm also open for any suggestions, so thanks for watching.